Right. Good morning, everybody, or good afternoon, whenever you're looking at it. Today we're going to have a look at a circuit. I presume you've looked at that video I put on earlier, which was about electricity and how it works. What I want to introduce you to today is the idea of a circuit, which is very, very important in your industry because you're dealing with circuits between Scottish Power, or the DNO, and between your customers. And those circuits need to be analysed and protected as much as possible by yourselves. So the idea of a circuit then is, we all know what a circuit is in real life. We might have a racing circuit, we might have a horse racing circuit, a running track or anything like that. And basically you start at a certain point, you go around the track and you come back to the origin again. And the same applies with electricity. If you're dealing with electricity, we have to have a complete circuit in order for something to actually happen. If the circuit becomes open, nothing happens. In other words, no lights come on, no transformers work, no switches work, no switchgear work, no solenoids work, nothing works basically if the circuit is open. In plumbing and gas it's a bit different, because in plumbing you open the tap, the water comes out, you can see it coming out and you can hear it coming out. Same with gas. With electricity it's a little bit different. We need to actually use special equipment to test whether we can see the electricity or not. So we start off with our basic circuit, which is a supply voltage. Then we have some kind of protective device to protect the circuit. Then we have a switch which controls the circuit, and then we have what we call a load, which is effectively your customers. So the substation really is the supply voltage. That is pushing through what we call a current, and that is I, and the resistance is present in the load. So we're going to come on to a little chart in a minute to explain that a bit more clearly. You've got a voltage, current, resistance, and that current going around the circuit produces two things. It produces a magnetic field right through the circuit, and it also produces heat in watts coming out of the load, and that's what we need to consider. It's quite important that you make a note of that circuit, jot it down in your notes, because it's a useful reference point. We'll be coming back to the idea of a circuit quite a lot over the next week or so. You also need to make a note of this chart. We have the volt, we have current, we have resistance, and we have power. The symbol is V for voltage, I for current in a circuit, omega for resistance, and P for power. Sometimes that's called E in some circuits. The unit is the volt for volts, amps for current, ohms for resistance, and a watt for power. When we're doing calculations for these, it's useful to have a little triangle. We can call that the resistance triangle, V, I and R. and also the power triangle, which I call this one power triangle. I can avoid knocking the camera. P, I and V. Okay. Now we can see an example of a circuit in action. Here we have a mock-up really of a circuit. I have my supply, which is coming from this black box here. This is the VS. It comes out of there, it comes out of the circuit, comes out of the power supply, through the switch, through the bulb, and back to the power supply. So we have a complete circuit there going around. I've actually put the switch in between, so there you can see when I switch the switch on and off, the light comes on and off. If I increase the voltage, I increase the pressure going around that circuit, increasing the current, and therefore increasing the brightness of that particular bulb. And actually the bulb will get hotter the more I apply a higher voltage, more current goes through it, and you get a higher dissipation of heat in watts, so it gets hotter. We'll be coming back to this board next week when we do resistors. The resistors that we're going to be dealing with next week are shown here, here and here, these three resistors, and they are effectively like deliberate resistances that you can put in a circuit in order to demonstrate voltage drop and current levels. Okay, so that's that. Come back to that next week. Right, so it's quite important when you're doing your calculations that you have these two triangles just as a bit of an aide-memoire and to help you remember. However, because we did transposition of formula the other day, in theory you shouldn't need these, you should be able to work them out, but they are just handy when you're just starting out on these calculations. It's handy to be able to just have these to hand. So we have a little example here of I draw 4 columns like this. I call that one voltage, that is current, that's resistance, and that's power. I'll do 3 examples, I think. So for example, if I have 12 volts and 4 amps flowing through the circuit, by looking at my little triangle here, I can work out resistance, because resistance is voltage divided by current. Voltage divided by current, V over I equals R. So I have voltage divided by 4 equals 3. So I know the resistance of this is 3 ohms. I can also work out the power from my power triangle. Power, when you're trying to work out the results from these triangles, all you do is cover up the letter that you're looking for, and in this case I'm looking for power, so I multiply current by voltage, okay, and I get I times V. Okay, and that comes to 4 12s is 48. If I have 2 amps and 8 ohms, I can now work out voltage, which is 16 volts, and the power,